Um, Hello, everyone. We're happy to have Lukas Kaufmann from Hamburg University as our first speaker. He will be talking about asymptotics of 5D supergravity theories and the Emergent String Conjecture. Please feel free to ask any questions during the talk. And as usual, we will leave the discussion open at the end of the second talk. Lukas, please go ahead.
Great. So thank you, George and Nacho, for inviting me and giving me the opportunity to present this work here. So the talk is based on this paper, which appeared last year together with Stefano Lanza and Timo Weigand. And the general framework of this talk is the swampland program, which aims to find characteristic features of quantum gravity theories. And one of the most well-known swampland conjectures is the distance conjecture, stating that at infinite distance in modular space, an infinite tower of states becomes light exponentially faster than the geodesic distance. And then some years later, this has been refined to the Emergent String Conjecture, which claims that the tower of states satisfying this distance conjecture consists either of K states or of the excitation modes of a unique, critical, and weakly coupled string. And so criticality implies that if we are in less than 10 dimensions, this has to be accompanied by a Kaluza-Klein tower at the same scale. And within various corners of the string theory and M theory landscape, there's a huge amount of evidence in favor of these conjectures. And what's crucial in most of these approaches is the geometry of the internal compactification space. And the question that we want to address today is what can be said without any further assumptions on the UV completion or also on some sort of internal geometry. There's been various approaches to this question, for example, based on black hole thermodynamics, graviton scattering, and also the weak gravity conjecture. Our approach will mostly be similar to this weak gravity conjecture approach. And the setup in which we want to ask this question is 5D n=1 supergravity. And within this setup, the main claim that I want to justify today is that every consistent such 5D n=1 supergravity with a non-compact vector multiplet modular space comes either from a 6-dimensional theory on a circle or from string theory. And to make contact with what I want to say later on, we established this claim by looking at the infinite distance limits in this modular space. And we find two sorts of limits. And in the limits where a theory looks like a 6D theory on a circle are the vector limits, where the gauge field, which becomes weakly coupled at the fastest rate, is a one-form gauge field. And on the vector multiplet modular space of 5D n=1, this one-form gauge field is furthermore unique. The string theory part we find in tensor limits, where the gauge field, which becomes weakly coupled at the fastest rate, is necessarily a unique two-form gauge field with at least one-form gauge field at the same scale. And in order to explain this in a bit more detail, I will first talk about some generalities of 5D n=1 supergravity. Then I will introduce the key players of our game, which are the supergravity strings, how we use them as probes, and what their 't Hooft anomalies look like. Then I will present our classification of infinite distance limits, and then I come to a quick conclusion. So 5D n=1, apart from the gravity multiplet, we find vector multiplets and hypermultiplets. The hypermultiplets will play no role, so we focus on the vector multiplet sector, which is determined by a real special geometry. So everything can be derived from a real prepotential, which we call curly F. And the most important terms in the 5D action for us are the kinetic terms for the one-form gauge fields with gauge kinetic matrix Fij. Special geometry tells us that this is given by this combination of derivatives of the prepotential. And then there's also this cubic Chern-Simons term with Chern-Simons coupling Cijk, and further terms which are not important for us. Importantly, this is the action at the two derivative level. At the two derivative level, as usual, we find corrections to this at higher derivatives. And the capital Latin indices run from 0 to the number of vector multiplets because we also include the graviphoton as some linear combination of these AIs. And then the vector multiplet modular space itself is parameterized by some scalars xi, which are subject to this hypersurface constraint. So the prepotential, which in 5D n equal 1 is given by Cijk xi is equal to a constant, which we choose to be 1. This is because f itself is a scalar in a hypermultiplet. And the BPS content on this vector multiplet modular space are BPS particles and BPS strings. The BPS particles have electric charge vectors Q with respect to the one-form gauge fields AI. And for future reference, I also note that the dual, so these charges form some cone, and the dual cone is what we call the Kähler cone. This does not refer to any internal geometry, it's just terminology. And if you want to look at the coupling of a BPS particle to linear combinations of U1s, we consider the physical one-form coupling, this fractal Q squared, which is given by contracting the electric charge vector of the particle with the inverse of the gauge kinetic matrix. For the BPS strings, we denote the magnetic charges with respect to the one-form gauge fields by P. These also form some cone. And again, if we consider linear combinations of U1s, we look at the physical two-form coupling, which in this case is given by the contraction of the magnetic charge vector with the gauge kinetic matrix itself. What will also be useful in our analysis is that electric-magnetic duality tells us that for the same linear combination of U1s, these physical one-form and two-form couplings are inversely proportional. Right, so among these BPS strings, there's a special subclass of strings which are called supergravity strings. These have been introduced in this earlier paper by Katzkin, Tarazzi, and Buffer. And the definition is that their charge vectors live in the closure of the Kähler cone. So just to have an example in mind, if the cone of BPS particle charges is given by those charge vectors with non-negative entries, then the cone of supergravity string charges is given by those magnetic charge vectors also with non-negative entries. And as has been argued in this original paper already, supergravity strings do not decouple from gravity. So on a conceptual level, this makes them ideal as probes of the gravitational sector of the theory and also in modular space. But more concretely, this non-decoupling from gravity will result in a very distinguished anomaly structure on the worldsheet of these supergravity strings. And so in general, we have our 5D bulk theory. If we place a solitonic string-like object in the background, the cubic Chern-Simons term will generate some gauge variance, which can be localized on the string worldsheet. And so this anomaly then has to be cancelled by degrees of freedom on the string worldsheet, which is just the general anomaly inflow mechanism. And if we compute this in the current setup for a string with charge vector P, then in the anomaly inflow polynomial I4, we find some term Fi wedge Fj, whose coefficient matrix K is called the Toft matrix. And it is given by contracting the cubic Chern-Simons coupling with the magnetic charge vector. And importantly, for us, it was very useful to think about this matrix K as a bilinear form on this vector space curly A, which is the vector space spanned by the gauge fields of the theory. An important property of this Toft matrix is that its eigenvalues correspond to the levels of abelian current algebras on the string worldsheet, which are again, which by themselves are given by the chiral zero modes. So we can look at the zero modes on the string worldsheet to learn something about the eigenvalues of this Toft matrix. And in various older papers, this has been done. So because a supergravity string does not decouple from gravity, we find one right-moving zero mode, which comes from the coupling to the graviphoton. And then for each vector multiplet gauge field under which the string is charged magnetically, we find a left-moving zero mode. So in total, this means that we find one positive eigenvalue and some negative eigenvalues, depending on how many vector multiplet gauge fields the string couples to, and then some zero eigenvalues. So in total, the signature of this 't Hooft matrix on a supergravity string is 1, r, where r is bounded by the number of vector multiplets. And the strategy that we follow in this talk and also in the paper is that we assume some mild form of the completeness hypothesis so that we can use the supergravity strings as probes. And enforcing this signature constraint, we can find consistency conditions on the CIJK, simply because by choosing this magnetic charge vector wisely and enforcing the signature, we find relations among the CIJK. And to see a first consequence of the signature constraint, we note that, first of all, compactifying the theory on a circle to 4D shows that the CIJK are quantized as integers. Then it has further been argued earlier last year that by looking at or by enforcing positivity of certain BPS and supergravity string tensions at the boundary of the Kähler cone, also the couplings of the form CIII and CIIJ have to be non-negative. And what we were able to do is to extend this to also include or basically all Chern-Simons couplings, so also with 3 distinct indices. And our arguments heavily rely on the signature constraint and then on the fact that this vector space together with this bilinear form looks like a Minkowski space. And with this result, we can build on earlier work, which tells us that all infinite distance limits in the current setup are actually weak coupling limits of some 1 forms or some 2 forms. Okay, and more generally, we find a lot of new constraints on the CIJK in this chosen basis of gauge fields, which are purely based on anomaly inflow. So we do not assume any UV completion. We don't talk about, or we don't need string theory, we don't need M theory, and we don't need some internal geometry. However, if the theory under consideration has a geometric origin, then all our constraints have very clear and precise interpretations in geometry. Just to give an example, the non-negativity of CIJK, which I showed on the last slide, is somewhat trivial in geometry, because in geometry these are just given by the triple intersection numbers among Neff divisors of an internal Calabi-Yau, and then this number is non-negative basically by definition. So once again, we find these constraints without relying on any potential geometric origin, so simply or purely from the EFT perspective. In particular, we can rule out certain EFTs by constraining the CIJK from the EFT perspective. And moreover, all of these constraints form the basis for our classification of infinite distance limits, which I want to present now. So in general, our infinite distance path will be parameterized by some affine parameter lambda, which we send to infinity. And then focusing on a simplicial subcone of the Kähler cone where all coordinates are non-negative, we parameterize the limit in a way that we single out a coordinate x0, which scales precisely as lambda to infinity, and all in such a way that all other coordinates scale at most like x0 in the limit. So some xa will go to 0, some may stay constant, some might diverge, but they cannot diverge parametrically faster than this x0 does. And then combining this non-negativity of the coordinates with the non-negativity of the CIJK, we find that in this prepotential, we only add non-negative terms. And then by enforcing this hypersurface constraint along the limit, shows that we need C00 to vanish, otherwise the expression for F will blow up. And so we can make a clear distinction of each infinite distance limit. So it is either of class A, in which case there is some direction I such that C00I is non-zero. And if that's not the case, C00I vanishes always, so for all I, in which the limit is called of class B. And so this is a straightforward classification of infinite distance limits. And the main part is how to relate these class A and class B limits to the asymptotic physics. And what we find is that all class A limits are vector limits, which, if you recall, means that the gauge field becoming weakly coupled at the fastest rate is a one-form gauge field. So in formulas, this means that the minimal physical one-form coupling squared is parametrically lower, smaller, that's the right word, than the physical two-form coupling for all supergravity string charges. And also special to this 5D n=1 vector multiplet setup, the U1 corresponding to this minimal physical one-form coupling is in fact unique and given by this linear combination. Class B limits are a little bit more complicated because they can be either vector or tensor limits, which depends on the scaling of the other coordinates in the limit. And just to give a quick flash of the definition of tensor limits, we have that there exists a unique supergravity string whose physical two-form is parametrically smaller than all other physical two forms corresponding to supergravity strings. And the scale of this minimal one matches the minimal one-form physical coupling squared again. And again, establishing these results depends on all the constraints predefined, and unfortunately these are quite technical, so it's it didn't seem too helpful to present these constraints here. But as a simple example, we can consider this prepotential where the only non-vanishing Chern-Simons couplings are C0 to 3 and C1 to 3. In the infinite distance limit, lambda goes to infinity with x0 and x1 scaling as lambda, while x2 and x3 scale as lambda to the -1/2. And then we can compute the physical two-form couplings corresponding to the charges delta I0 and delta I1. We find that both scale as 1/λ in the limit, so go to 0. And if we assume the existence of supergravity strings with these charge vectors, then we also find that the corresponding tensions will go to 0 at this rate. And one can also check the physical one-form couplings, but it seems that in this limit, two emergent strings with charge vectors p and p prime become tensionless at the same rate. So it appears already this simple example evades our classification, and in particular seems to potentially violates the emergent string conjecture. Luckily, the answer is no, and the answer is no because the prepotential does not satisfy all the constraints. What this means concretely is that we have a non-vanishing C0 to 3. And by our constraints, this should be proportional to some non-zero number times C0, 1, 3. But we know that C0, 1, 3 vanishes in this case. Hence, this is a contradiction. And the prepotential is, in fact, not well defined. We can make it consistent by adding a non-zero C0, 1, 3. Then the prepotential looks like this. And what this new term tells us that the previous infinite distance limit needs to be modified. Previously, x3 scaled as lambda to the -1/2. However, looking at this term, this would grow like lambda to the 3/2 in the limit, so it would explode and violate the hypersurface constraint. To prevent this, x3 has to scale at most like lambda 1/λ squared. And what we find as a result of this is that the limit is in fact well-defined and a vector limit instead of some sort of emergent or tensor limit. So we see that our constraints took care of this ill-defined prepotential and in fact got rid of this sick-looking infinite distance limit. Okay, so what I've shown you earlier works more generally. And to make now contact with our original motivation, which was the emergent string conjecture, we can actually compute the scaling of this minimal physical one-form coupling in vector limits. We find that it scales as 1/λ squared. And then by employing the hypersurface constraint along the limit, we find that expressed in the geodesic distance on the modular space, it decays exponentially, as is expected by the distance conjecture. And furthermore, we find that the coefficient with which it decays is precisely the one expected for decompactification from 5D to 6D. So in this sense, our vector limits are decompactification limits to 6D. And we can do the same thing for our tensor limits, where we compute the square root of the minimal physical two-form coupling. Expressed in the geodesic distance, again, this looks exponential, and the coefficient in front is the one expected for emergent strings in 5D. So our tensor limits look like emergent string limits. And if you recall, with what I've told you so far, we've seen that in a general 5D n=1 supergravity, all our infinite distance limits are either decompactification or emergent string limits. And furthermore, I've only told you that, but yeah, did not provide the details. This emergent string is necessarily unique with this charge vector, and it is weakly coupled. So all that is left basically is the criticality of the emergent string. And this is in fact also what we are still missing. So if we assume a geometric origin of our supergravity theory in terms of M theory on the Calabi-Yau threefold, then the criticality of the emergent string is established in two steps. The first is by constraining the second Chern classes of the surface fiber, because the emergent string comes about as an M5 brane wrapping the surface fiber, and one finds that it has to be either 0 or 24. And then there are various string dualities relating it to a type 2 or a heterotic string. Interestingly, the second Chern class of the surface fiber also enters the supergravity as part of an additional Chern-Simons, or as part in form of a Chern-Simons coupling, which is part of a higher derivative correction. And the criticality of the emergent string can then, at least at the moment, be stated as this sort of conjecture. So as soon as we are in the supergravity with C0, 0i being 0 for all I, this C0 has to be constrained to be either 0 or 24. What we currently know, mostly following arguments from this paper again, which is just the unitarity of the worldsheet theory, we can say that C0 has to be a non-negative multiple of 12. So this luckily includes the critical values, but obviously many, many more, which we want to exclude in the future somehow. Okay, and so to conclude, I hope I'm still in time. Okay.
Yes, you're in time, yes.
Okay, so we used anomaly inflow on supergravity strings, and with the resulting constraint on the 't Hooft anomaly matrix of these supergravity strings, we were able to classify all infinite distance limits in the vector multiplet space, multiplet modular space of 5D n=1 supergravity. And we found that there could only be vector or tensor limits, which very much mimic the notion of decompactification or emergent string limits. And in this sense, we've justified our initial claim that every consistent 5D n=1 EFT with a non-compact vector multiplet modular space comes either from a 6-dimensional theory on a circle or from string theory. As I mentioned earlier, an open question involves the criticality, phrased in terms of this conjecture. So the goal is to constrain C0 to be either 0 or 24, which would not provide criticality, but just a further hint at it. And of course, one can see how much of the story plays out in other dimensions and maybe even with less supersymmetry. And I think this is all I wanted to say. So thank you.
All right, let's thank Lukas for his great talk. Are there any questions from the audience? If yes, please unmute yourself and ask.
Hi, I do have a question. Thanks, Lucas, for the very nice talk. I have my question is: are you able to see like from the just from the EFT data? Are you somehow able to like classify or quantify how many like the arrangement of like these either the compactification to 60 or emergency limits you can have?
So you mean given a supergravity, how many limits I could take?
Yeah, and like to see how I have 20 of one type and 3 of the other. Or do you have like any constraints
Um,
on that?
so in principle, the type of limit you can take, you can read off directly from the structure of this cubic Chern-Simons term. We have a list of constraints that need to be satisfied in this certain set of limits, and if the given EFT satisfies these constraints, you can take this limit. And if I understand your question correctly, you can just check for these constraints in the action, and this will tell us what limits you can take and how many of them you can take.
Okay, thanks.
Any other questions from the audience? We will leave the discussion open in any case, so if you want to ask Lucas a question, you can do it later if you want. All right, then let's thank Lucas once again, and we can move on to